Until Voyager arrived in the Neptunian system, this was the least understood of all the planets. Invisible to the naked eye, Neptune was a world hidden from view. Even through the most powerful of telescopes, it appeared as no more than a blurry ball of blue and green. The fourth largest planet in the solar system by volume, and the third largest by mass. From afar, we knew nothing of its atmosphere or its structure, and had only faintly observed two of the moons in its orbit, Triton and Nereid. This was a planet that had remained very firmly in the darkness, a distant world that had clung on tightly to its secrets for over 140 years. Even the discovery of Neptune played out in the darkness. The last of the planets to be discovered, it is the only one whose existence we predicted before it was ever observed by the human eye. For centuries we stared at it without knowing what we were looking at. Almost certainly, Galileo was the first human to peer at Neptune directly, during a series of observations at the end of 1612 and the beginning of 1613. The data he plotted with his newly invented telescope led him to believe this was a fixed star in the night sky, not a planet. Over the next 200 years, many astronomers must have fixed their gaze on this dim star without realizing the significance of its bluish light. But the first hint of its true nature would appear not in an eyepiece, but in a set of astronomical tables. In 1821, the French astronomer Alexis Bouvard published Tables astronomiques, a set of tables predicting the orbits of the three outer planets, Jupiter, Saturn, and Uranus, based on Newton's laws of motion and universal gravitation. Over the next few years, Bouvard's theoretical work would be tested against the movements in the night sky, and his painstaking calculations were rewarded with the confirmation that actual observations of the movements of Jupiter and Saturn adhered precisely to his mathematical predictions. However, Uranus refused to behave quite so compliantly. The movement of the then farthest planet deviated substantially from Bouvard's predicted path, and this led him to make a wild suggestion. Either Newton was wrong, or perhaps there was an as-yet undiscovered planet lurking in the darkness, distorting the passage of Uranus through its gravitational interaction. A flurry of astronomers sped to find the hidden planet, the ultimate prize for any stargazer, as an acrimonious race kicked off between the British and French to predict the planet's location. On the British side of the Channel, the Cornish astronomer and mathematician John Couch Adams became obsessed with Bouvard's hypothesis and was convinced he could use nothing more than pen and paper to determine the size, position, and orbit of this hidden world. By September 1845, Adams had at least partially completed his calculations, but unknown to him, almost simultaneously, the French mathematician Urbain Le Verrier in Paris was completing his own complex computations of Uranus's path and the elusive eighth planet. By the summer of 1846, Le Verrier had played his hand and announced to the Académie des Sciences on the 31st of August that he had calculated a predicted location for the missing planet. Revealing his work just 2 days before, Adams secretly sent his own prediction in a letter to the Royal Greenwich Observatory for verification. In what must be one of the most close-run races in scientific history, Le Verrier engaged the Berlin Observatory in the search for his planet, and at 00:15 on the night of the 24th of September 1846, Johann Galle, with the help of his assistant Heinrich Darré, looked through his refracting telescope and became the first person to knowingly gaze at the eighth and furthest planet in the solar system. A planet that had taken decades to locate was found in less than an hour, and within 1 degree of the position Le Verrier had calculated. Even today, the exact credit for the discovery of Neptune is still disputed, but in the winner-takes-all world of astronomical discovery, it's Le Verrier whom history records as the discoverer of Neptune, the man who discovered a planet with the point of his pen. It took another 143 years before we would visit Le Verrier's planet and witness a dynamic, violent and volatile world. As Voyager drew closer, it began to return a precious set of images that remain to date our only close-range record of this planetary system. At first flying past Nereid, the third largest of Neptune's moons, Voyager captured our only image of this distant world travelling on its massively eccentric orbit around the planet, But it was the images of Neptune itself that became increasingly astounding. Painted across the surface of the planet, Voyager revealed banks of methane clouds that were being whipped around by high-altitude winds at speeds of over 2,000 kilometers per hour. At least 5 times stronger than the most powerful winds ever measured on Earth. These were the highest wind speeds we'd witnessed anywhere in the solar system. It wasn't just violent winds that we saw through Voyager's eyes. Great hurricane-like storms could be seen moving across its surface, the largest being an Earth-sized storm system similar to the Great Red Spot on Jupiter, which became known as the Great Dark Spot. Voyager took multiple images of this vast storm system as it sped past the planet, skimming the cloud tops of the northern pole from a distance of just 4,400 kilometers as it reached its nearest approach on the 25th of August 1989. No one had expected such massive storms to be brewing so far from the Sun. But just 5 years later, with the Hubble telescope up and running, we peered back towards Neptune and found that the Great Dark Spot had disappeared. Unlike the giant storms on Jupiter, which we've witnessed playing out for centuries, it seems that the weather on Neptune is far more transient, with the largest events coming and going within the space of a few years. The intense weather systems that we witnessed on Neptune remain a tantalizing puzzle. The planet is on average 50% further from the Sun than Uranus, and receives just 40% of the sunlight that hits its sister world, and the surface temperatures of both planets are equally intensely cold. In fact, the temperature of Neptune's outer atmosphere is one of the coldest places in the solar system, with temperatures at its cloud tops measuring around minus 220 degrees Celsius. Orbiting this far out in the far frozen reaches of the solar system explains the blandness of Uranus's weather. But why would Neptune, even further from the Sun, be so active? The answer, we think, lies in a mysterious and powerful source of heat that we have detected coming from deep within the planet. All of the planets, including Uranus and Neptune, have some residual heat locked deep inside them, and much of this is the thermal energy that remains from the endless collisions of their creation, as well as the heat released by the radioactive decay of certain elements in the core. However, this far out, Uranus has rapidly lost this heat, and today radiates just 1.1 times the energy it receives from the Sun, so that the heat radiating from its core is too little to drive any kind of dynamic weather system through its atmosphere. Neptune, it seems, has a far warmer heart, and Voyager was able to reveal that the most distant planet radiates 2.61 times as much energy as it receives from the Sun. It's these unexpectedly high temperatures that help to explain the violent storms we see in its atmosphere. As the heat makes its way from the core of the planet and out into space, it churns up the entire atmosphere, creating winds of extreme ferocity, and once they start, there is little to stop them. Neptune, like Uranus, is an ice giant, a planet composed of a rocky core and a mantle made up of water, ammonia, and methane ices, surrounded by a cold gaseous atmosphere. With no solid surface on the planet, there are no mountains or continents to break up the flow of the atmospheric gases, so this means the winds can whip around the planet, picking up speed until they are quite literally supersonic. All of this helps to give us a reason for Neptune's extreme weather, but not an explanation. Voyager 2 was unable to reveal why Neptune and Uranus are so different, and we still don't know what it is about these planets' formation that left Neptune with far more residual heat, making it the far more active of the two. Neptune's active atmosphere was not the only surprise Voyager returned to us with the pictures from its two-camera system. In vibrant and vivid detail, the images also revealed the solar system to be home to not one, but 2 blue planets. Neptune is a bright blue world, but with no liquid water on its surface, we know that the origin of this color cannot be the same as here on Earth. This deep cobalt color must be produced by something else in Neptune's atmosphere, and Voyager provided the answer. Using its onboard spectrometer, Voyager was able to measure for the first time the composition of Neptune's atmosphere, and found it to be comprised of 80% hydrogen, 18.5% helium, and 1.5% methane. Methane was by far the smallest component. Yet this is the key to understanding Neptune's blue hue. The light of the sun contains all the colors of the rainbow, but as it hits the surface of a planet, it interacts in different ways depending on the molecules it encounters. In the case of the Earth, the water that covers our planet absorbs all of the red light in sunlight, so as the sun strikes the surface, only the blue is reflected back. It's the same with all the plants on our planet. The chlorophyll absorbs the blue and red light, so that only green is reflected back. On Neptune, there is no water to turn the planet blue. Instead, it's the methane that absorbs the red light of the dim and distant sun, reflecting the blue light back out into the darkness. But things aren't quite as simple as they first appear. Uranus is also a blue world, but just that bit paler and greener in shade compared with its more distant sibling. And yet Uranus also has methane in its atmosphere. In fact, it has slightly more. So Uranus, not Neptune, should be the darker shade of blue. Why is this? Well, quite wonderfully, we still don't know. Voyager looked for other constituents in Neptune's atmosphere that could account for the deeper blue, but it found nothing that could explain the discrepancy. So for now, the many differences between these two worlds remain a mystery. After over 12 years of travelling, Voyager 2 completed its grand tour of the solar system. A tiny explorer that had set out from Earth and travelled across 7 billion kilometres of space on a single extraordinary journey to explore all of the outer worlds of the solar system: Jupiter, Saturn, Uranus, and Neptune. But before it began its long, lonely journey into the darkness of interstellar space, there was one more brief rendezvous left on its itinerary. While in the Neptunian system, Voyager had made endless discoveries, including the detection of a faint ring system and the confirmation of 6 new moons in orbit. But in those final hours of close contact, as it flew across the north pole of the planet, the mission scientists back at JPL had instructed the craft to make one last intrepid maneuver: a close flyby of Neptune's giant moon, Triton. Just 5 hours after nearly touching the cloud tops of Neptune, Voyager travelled within 40,000 kilometres of the Neptunian moon and returned the first pictures of this strange and distant world. The British astronomer William Lassell first spotted Triton on the 10th of October 1846, just 17 days after the discovery of Neptune. As astronomers clamoured to observe the newly identified planet, it was Lassell with his homemade telescope who noticed the satellite first. Although not officially named until many years later, Triton would remain the only known satellite of Neptune for over 100 years, until the discovery of Nereid by Gerard Kuiper, more of him later, in 1949. As Voyager returned the first images of this distant moon, it immediately became apparent that, just like Neptune, Triton was far more active than we had ever imagined. Here in the furthest reaches of space, the 7th largest moon in the solar system was far from a frozen, inactive rock. It was a geologically active world, with features unlike anything we had imagined. Able to image just 40% of its surface due to the fact that most of the northern hemisphere was in darkness, Voyager revealed Triton to have a sparsely cratered exterior, with a strange network of ridges and valleys covering its entire surface, including in the western hemisphere a region dubbed the Cantaloupe Terrane, because of its striking similarity to the skin of a melon. All of this evidence pointed to the fact that the surface of Triton was young, not battered and ancient like that of our moon, a surface that, even though it had been recorded by Voyager's instruments as one of the coldest places in the solar system at -235 degrees Celsius, seemed to be being resurfaced by active volcanism occurring across the planet. But this was not volcanism as we understand it here on Earth. There is no molten rock beneath the surface of Triton. This is an ice world, with a surface covered in a frozen mixture of nitrogen, water ice, and carbon dioxide. Any volcano that exists here would be a cryovolcano, erupting water, ammonia, and methane from below the surface. Cryomagma that would immediately solidify in the extreme low temperatures at the surface. And as Voyager peered closer at the surface of Triton, It captured a series of images of the southern polar region that appeared to provide evidence of such geological activity. Lurking amongst the flat volcanic plains and rift valleys was a set of distinct features that at once caught the eye. Scattered across the surface were what appeared to be at least 50 dark plumes. Voyager was traveling so fast and so far away from the Moon that it was unable to get close-ups of these intriguing plumes, but we are certain that they are the evidence of ice geysers, and that the dark streaks are dust deposits left on the surface by the eruption of these geysers. According to planetary scientist Noah Hammond, it was a big surprise to see active geysers going on Triton, shooting 8 kilometers into the air, and we think these geysers might be forming as a result of nitrogen ice which is being vaporized by the sun. Both of the geysers that Voyager 2 observed, which are currently blowing up, are concentrated on the warmest part of Triton, where the sunlight is striking the hardest. And as the sunlight pierces through the nitrogen ice, it starts to turn that nitrogen ice back into a gas again, and that gas builds up and builds up until it has enough energy to break through the ice and lift dust all the way up into the atmosphere. Further analysis of the images suggested that at least 4 of these geysers were active at the time of Voyager's flypast, belching clouds of ice and dust 8 kilometers up into the thin Neptunian atmosphere before falling back down to the surface over 100 kilometers downwind. Perhaps even more astonishingly, we have been able to actually formulate a hypothesis for the mechanism that lies beneath them. The key to understanding why this wondrous geological activity occurs in the most unlikely of places seems to involve their location on the surface of Triton. From the imaging data that Voyager 2 returned, it seems the geysers tend to erupt on the most sunlit part of Triton's surface. From a distance of 4.5 billion kilometers, the sun's rays are faint, and the amount of thermal energy landing on the surface is low. But combined with the specific chemistry on Triton's surface, the effect of the sun can still be dramatic. What seems to be happening is that sunlight falling on the thin layer of nitrogen ice that covers Triton is penetrating the surface and heating up a layer of darker methane particles a meter below the surface. The methane acts as a subsurface greenhouse gas, trapping the heat below the surface and radiating that heat back up through the frozen nitrogen. Even though this mechanism creates a temperature difference of just 4 degrees Celsius between the ambient surface temperature and that of the warmer interior, this difference is enough to melt the frozen nitrogen and create pockets of gas. Sitting beneath the nitrogen ice, that gas is kept under pressure, building up until ultimately it punches through the nitrogen ice, creating the geysers of Triton and carrying the dark ice particles up to 8 kilometers into the sky. Although the faint light of the sun is just strong enough to power Triton's geysers, it's simply too weak to have driven the other geological processes that have created the network of valleys and crevasses we see all across the surface. It seems that something in Triton's past must have heated the Moon enough to drastically alter its terrain. And a potential clue to the source of that ancient heat can be found in the oddity of Triton's orbit. Unlike every other large moon in the solar system, Triton orbits in the opposite direction to the spin of the planet. Travelling around Neptune in its tidally locked orbit, with the same side facing inwards at all times, Triton orbits in a clockwise direction, while Neptune spins on its axis every 16.11 hours, anti-clockwise. Such dissonance between planet and satellite suggests that it is very unlikely that Triton and Neptune formed at the same time. A planet and moon system fashioned from an identical collapsing cloud of gas and dust at the same moment would tend to spin and orbit in the same direction as the spin of the initial dust cloud, just like the overwhelming majority of moons we see in the solar system today. So the most likely explanation is that Triton joined Neptune much later, a visitor to the Neptunian system that, unlike Voyager, never left. Like Uranus, we don't know for certain the deep history of Triton, but all the evidence from its orbit and surface features point to the possibility that long ago Triton was not a moon at all. To understand where it might have come from, we need to look beyond the Neptunian system and peer further out into the darkness. It was only relatively recently that we confirmed the existence of a region of the solar system now known as the Kuiper Belt, a disk of millions of objects that stretches out from the orbit of Neptune to at least 50 AU from the Sun. Similar to the asteroid belt in structure, but far larger in scale. We had long speculated that such a region might exist, but it wasn't until the discovery of an icy object known as 15760 Albion in 1992 that we were able to put together a body of proof. The discovery of this region was a turning point in our knowledge about our solar system. According to Alan Stern of the New Horizons mission, the Kuiper Belt was so revolutionary because, as it's so far from the Sun, the temperatures out there are almost absolute zeros, so everything is so well preserved. It's an archaeological dig, if you will, into the early history of our solar system. So it's a scientific wonderland, and you put all that together, redrawing the map and putting us in our place about who's the oddball now. It's not Pluto, it's the Earth or Jupiter that's the oddball. And then having this museum piece place in the solar system where everything is so well preserved, I can't think of a bigger discovery that we've made that's reshaped our thinking so profoundly in all the decades of space exploration. Albion was the first trans-Neptunian object to be identified since the discovery of Pluto and its moon Charon. And this finding launched a flurry of further revelations that now put the number of identified objects in the Kuiper Belt region at around 2,400. We think there are at least 100,000 objects bigger than 100 kilometers wide in the Kuiper Belt. Just like the asteroid belt, this dispersed region of debris is composed from the remnants of our solar system's formation. But whereas the asteroid belt is a disk of rocky fragments, we think the Kuiper Belt is made up of icy objects, with methane, water, and ammonia the major ingredients. And it's that list of ingredients that leads us back to Triton and its strange history. We believe now that perhaps only Triton grew up out in the Kuiper Belt, amongst the millions of other frozen lumps of water, ammonia, and methane circling the Sun, before something such as a collision disturbed its orbit and flung it inwards. Plucked from the Kuiper Belt, Triton would be captured by the gravitational pull of Neptune and forever trapped in its strange orbit around the blue planet. Today, Triton orbits in a nice regular circle around Neptune, a bit like the way that our moon orbits around the Earth. But to begin with, this newly captured satellite would have almost certainly been in a chaotic orbit. Glancing past the planet, it would have started along a wide elliptical path around Neptune, bringing it from far out to close in on every revolution. This would have meant that as Triton orbited Neptune, the gravitational pull would be constantly changing, stretching and squashing the moon just as Jupiter does to Io today, with the result that the friction of these tidal forces would have heated up the interior of Triton, creating far more activity than the erupting geysers we see today. Through this process of tidal heating, the ancient interior of ice would have become molten and volatile, exploding up through cracks and faults in the moon's crust, creating the ragged surface we see today. Over time, as the orbit adjusted into a more regular circular path, the friction reduced, the heating diminished, and so what we're left with is an icy, frozen moon circling the wrong way around its planet, the subtle scars of its early life written across its surface. All that remains today of that dramatic, violent past are the geysers, powered by the faint light of the sun, painting dark streaks across the now quiescent surface. As Voyager 2 sped away from Triton and Neptune at over 60,000 kilometers per hour, the planetary exploration phase of this extraordinary mission finally came to an end. Its exploration would continue beyond even the furthest reaches of our solar system, and would extend into the unknown depths of interstellar space. But its time as a planetary explorer was over. A tiny spacecraft, built with 1,000 human hands, had shone a light into the darkness, revealing the secrets of worlds that had been hidden in the night for over 4 billion years. As yet, we have not returned. But while Neptune and Uranus have fallen back into the distance, viewed only through the lenses of our most powerful telescopes, another, even more distant world was out there waiting for our first arrival. On the night of the 23rd of January 1930, a 23-year-old junior researcher at the Lowell Observatory in Flagstaff, Arizona, took an image of the night sky using a 13-inch astrograph, a telescope designed for the sole purpose of astrophotography. Clyde Tombaugh had been at the observatory for just over a year when he took the image, one of hundreds he had captured over previous months. A keen amateur astronomer, he had landed this first job after sending in a series of drawings he had made of Jupiter and Mars using telescopes he had built at his home. Every night at the Lowell, Tombaugh performed the same task, using the astrograph to photograph a precise section of sky that he would then image again a few nights later. The task was a little laborious, but its purpose was profound, because hiding within the near-identical images, Tombaugh was on the hunt for a new world, the enigmatic Planet X. Unless we think hard, our intellects are confined to the surface of the Earth. After sunset, beyond cities, the universe appears, a destination for the imagination, albeit separated by a seemingly unbridgeable gulf. This may be true for the stars, but it is not so for the planets. There are times when Mars, Venus, Jupiter, and Saturn dominate the sky, bright lights that shift position nightly against the fixed stars, commanding our attention even if we aren't certain what we're looking at. The distances are still vast by terrestrial standards, but despite appearances, the gulf is certainly not unbridgeable, because we have visited all of these planets and taken our first steps into the outer reaches of the solar system beyond. And yet the wandering lights in the dark still feel detached from human affairs, and the time and effort we've spent in visiting them might seem to be an indulgence. This assumption, however, is profoundly wrong. The solar system is a system. The Sun and the 8 major planets and countless billions of minor planets, moons, asteroids, comets, and unclassified lumps of ice and rock were formed back in the mists of time, and they continue to evolve as one. We rarely notice the dynamic, interconnected nature of our system, although asteroid strikes on our planet are not such a rare occurrence. The Chelyabinsk impact in February 2013 injured 1,500 people when a 12,000-ton asteroid broke up as it entered the Earth's atmosphere at 60 times the speed of sound, and the Tunguska airburst in Siberia in 1908 flattened 800 square miles of forest in an explosion comparable to that of the most powerful hydrogen bomb ever tested. The surface of the Moon bears testament to a record of violence and destruction from the skies that the Earth has also endured, but the relentless erasure of craters by weathering, and our good fortune that no major impacts have occurred in recorded human history, are the reason for our misplaced sense of isolation from the heavens. The interdependent nature of the solar system has become more evident as we've begun to understand its history. It's tempting to imagine that the physical layout of the planets is a fossilized remnant of primordial patterns in the collapsing dust cloud around the newly ignited Sun 4.6 billion years ago. But our exploration of the planets, coupled with increasingly powerful computer simulations of the evolution of the solar system, has revealed that this is not the case. Planetary orbits are prone to instability, particularly so in the early, more chaotic years when our solar system was young. The details of precisely how the planetary orbits have shifted are still uncertain, but we now suspect that Mercury, the innermost planet, began life much further out and was deflected inwards to its present-day seared orbit. Jupiter and Saturn may have drifted inwards shortly after their formation, before reversing their course and retreating, but not before affecting the distribution of material out of which Mars and Earth would later form. Around the time that life began on Earth, Neptune and Uranus may have been flung outwards, disrupting the orbits of billions of smaller objects far from the Sun. The record of this time of unprecedented violence, known as the Late Heavy Bombardment, is written across the scarred surface of the Moon, itself most likely formed in a glancing interplanetary collision between Earth and a Mars-sized planet 4.5 billion years ago. The planets are like snowflakes. The detail of their structure, their composition, size, spin, and climate are a frozen record of their past. An understanding of the planets beyond Earth is therefore a prerequisite for understanding our home world, and that, in turn, is a prerequisite for understanding ourselves. Earth is unique in the solar system because it's a planet with a complex ecosystem. The genesis and subsequent 4 billion-year evolution of life on Earth required planetary characteristics which are necessarily linked to the evolution of the system as a whole. There had to be liquid water on the surface, and much of this water was delivered after the Earth's formation by icy, water-rich asteroids and comets, possibly deflected inwards from the outer solar system by Jupiter. These rivers, seas and lakes of extraterrestrial origin had to persist for the best part of 4 billion years, which required a stable atmosphere to maintain surface temperatures and pressures within a limited range. 4 billion years is a long time, around a third of the age of the universe. The Sun has brightened by 25% since the Earth formed, which makes the stability of our environment all the more difficult to understand. In a chaotic system of planets around an evolving star, a planet with life-supporting properties and the remarkable stability enjoyed by Earth over billions of years may be extremely unusual. The study of our sister worlds, Mars and Venus, has proved instructive in understanding just how fortunate we may have been and how delicate our position today might be. 4 billion years ago, as life began on Earth, Mars was also Earth-like. It had oceans and rivers, an active geology and complex surface chemistry, the ingredients of life. One of the primary goals of the fleet of spacecraft currently in orbit around and exploring the surface of Mars is to search for evidence of past or even present life, and to understand why the red planet was transformed from a potential Eden at the dawn of the solar system to the frigid desert world we observe today. The story is complex, but one of the most important differences between the two worlds is size. Mars is just 1/10 the mass of Earth, too small to hang on to its internal heat, its protective magnetic field, and its atmosphere for much more than 1 billion years after its formation. Yet Mars formed in a similar region of the solar system to Earth and Venus, so why is it so small? The answer may lie in the fast-changing orbits of Jupiter and Saturn early in the solar system's history. The history of Venus is perhaps even more puzzling, in part because of the immense difficulty of exploring the planet. Venus is often described as a vision of hell. Surface temperatures are high enough to melt lead, and the atmospheric pressure is 90 times that on Earth. Sulfuric acid raindrops fall from its clouds. And yet, long ago, Venus too may have been Earth-like. Perhaps there were once Venusians, before a runaway greenhouse effect took hold and began destroying Venus's temperate climate about 2.5 billion years ago, although this date is highly uncertain. Taken together, the stories of the 3 large terrestrial planets are salutary. If an alien astronomer observed our solar system from afar, they would classify Mars, Earth and Venus as potentially living worlds, orbiting as they do inside the so-called habitable zone around the Sun, the region within which, if atmospheric conditions are right, liquid water can exist on the surface of the planets. All 3 worlds may once have been habitable, and all 3 worlds may once have harbored life, but now only Earth supports a complex ecosystem, let alone a civilization. Understanding why Mars and Venus diverged so significantly from Earth over the last 4 billion years will provide great insight into the fragility of worlds, and perhaps suggest whether our own good fortune is near impossible to comprehend or merely outrageous. Planets change. Ours could change at any moment. A stray comet from the frozen Kuiper belt beyond the orbit of Neptune could put an end to our story. We could also put an end to ourselves. The study of Venus might help us avoid one of the ways by which we could destroy our civilization, because it shows us what greenhouse gases can do to a world. I think one of the reasons why anthropogenic climate change is so difficult for a certain type of person to accept is that atmospheres seem ethereal and tenuous. and incapable of trapping enough heat to modify the temperatures on a planet significantly. For such people, I suggest a trip to Venus, where they will be squashed and boiled and dissolved on the surface of Earth's twin. The exploration of the planets, then, is not an indulgence. If we want to know how we came to be here, we need to understand the histories of the planet that gave birth to us, and the system that gave birth to it. We are children of Earth, and also children of the solar system. Understanding our history is important because it places our existence in context. The more we learn about the events that led to the emergence of humans on this planet only a few 100,000 years ago, the more we are forced to marvel at the sheer unlikeliness of it all. We needed Jupiter and the comets and asteroids and countless collisions and mergers and near catastrophes stretching back 4.6 billion years. There are valid objections to this way of thinking. It is an objective fact that we are here, and our future should be our primary concern. That may be so, but I argue that a deeper understanding of the evolution of the planets is essential for our continued prosperity and existence on this one. The threat of catastrophic climate change is an obvious example, but there are many other reasons why knowledge is important. There is feedback in human affairs. Our collective state of mind affects the decisions we make. To confine our imaginations to the surface of the Earth is to ignore both our immense good fortune and the fragility of our position. A wider knowledge of both will, I believe, help secure a safer and more prosperous future. Earth sits a mere 150 million kilometers from the Sun. Not too hot, not too cold, with surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change color to become a red giant. Small stars, like our Sun, will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning. At first the changes will be invisible, but 1 billion years from now they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapor from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the sun comes through pretty much unimpeded by an atmosphere and reaches the surface of a planet. Then the surface of the planet re-radiates that radiation in infrared, because planets are much cooler than the sun. And that means they radiate at much longer wavelengths, what we call infrared or heat radiation. That infrared radiation doesn't make it through an atmosphere so easily. Some of the atmospheric gases, the ones we call greenhouse gases, block infrared radiation, and so therefore the more of those greenhouse gases that are in a planet's atmosphere, the harder it is for that surface radiation to make it back out into space, and the more that planet will heat up. Estimates of the timescale that will see our oceans disappear vary massively, and are heavily influenced by a multitude of factors. But few are in doubt that by the time our planet reaches its 8 billionth birthday, in 3.5 billion years' time, the end will be in sight. With temperatures heading above 1,000 degrees, life will have long disappeared from a surface that is beginning to melt under the burning sun. Moving even further into the future, the outlook becomes bleaker. As the sun enters old age, it will grow into a red giant, engulfing the Earth within its expanding atmosphere. Moonless, lifeless, and perhaps reduced to its inner core, our planet and the civilizations it once harbored will be nothing but a distant memory, etched in the atoms that made us all, as they are dispersed amongst the cosmos. For planet Earth, the clock is ticking, and time is slowly running out. But ours is far from the only world to enjoy its moment in the sun. Across the history of our solar system, stretching deep into its ancient past and reaching far into its future, we see stories of worlds in a constant battle with our ever-changing star. Close in, ancient worlds such as Mercury, which long ago lost their fight with the sun, are taunted by views of Earth and what might have been. Further out and even hotter, Venus circles, shrouded in a choking cloak of cloud, and even further beyond the Earth, Mars sits cold and barren. Beyond these planets, frozen worlds await, huddled in perpetual hibernation, anticipating the moment when the warmth of the sun reaches out far enough, with sufficient heat, to trigger a first spring. On that day, mountains of ice will melt, rivers of water will flow, and where there was once only bleakness, in the distant future on planets once frozen and lifeless, we might find a place that looks very much like home. The story of our solar system is not as we once thought it, eternal and unchanging. Instead, it is a place of endless transformation. It is a narrative that repeats itself with a predictable rhythm. As one world passes, another comes into the light. Only one planet has maintained stability for almost the entire life of the solar system. The Earth has remained habitable for at least 4 billion years, while change has played out all around it. What makes the Earth so lucky compared to all of its terrestrial siblings? To answer that question, we need to look not just at our planet, but at the whole of the solar system, going right back to the very beginning. For the first few million years after its birth, there were no terrestrial worlds to see the sun rise, and there were no days, no nights, no circular tracks around it. Instead, surrounding our infant star was a vast cloud of dust and gas. A tiny fraction of the material left over from the sun's formation. This swirling cloud would one day coalesce to form the various planets of the solar system, and many other smaller bodies. But at this time, 4.7 billion years ago, there was nothing but tiny specks of dust reflecting back the light of our slowly growing star. Only time, vast amounts of empty time, would allow enough of this gas and dust to catch and cluster, randomly forming the smallest of seeds. Most of these seeds would hardly get the chance to grow at all, smashed apart and returned to the immense swirl of dust from whence they arose. Just a few would grow big enough and survive long enough to capture and condense more of the cloud, slowly increasing their mass and density. We still do not fully understand the process by which grains of dust no thicker than a human hair can amass to become rocky objects the size of a car. and as yet no model exists to explain this part of the evolution of a planet. But what we do know is that once that disk of gas and dust becomes populated with clumps of rock that make it past the meter-sized barrier, a powerful force comes into play to propel the process forward. These newly formed planetesimals are big enough to allow the great sculpting force of gravity to draw the clumps together, growing to sizes of over 1 kilometer in length. Swirling around the sun, thousands upon thousands of these objects live and die, colliding and coalescing under the increasing gravitational forces of attraction, until eventually just a few emerge as planetary embryos, moon-sized bodies known as protoplanets. In the last violent stages of the process of planetary birth, these protoplanets swirl around in crowded orbits, and many are destroyed, returned to the dust of their origins. But occasionally, when a collision brings 2 or more of these giant objects together, the size of this mass of rock becomes big enough for gravity to pull it in from all sides, creating a sphere of newly formed rock, a new world. In that moment, a planet is born. Each of the terrestrial planets in our solar system was born this way. They are the survivors of a process that destroys far more worlds than it ever creates, and which left just 4 rocky planets remaining, starting closest to the Sun with Mercury, then Venus, Earth, and finally, farthest out, the cold and dead world of Mars. Today, these 4 worlds all look vastly different, and yet all were created the same way, made up of the same ingredients and orbiting the same star. So why have they ended up so distinct from each other, and with such starkly different environments? And what makes this place, the Earth, so unique, the only one of the rocks that has blossomed with life? To understand, we have to look deep into the past of our solar system, to explore the unique history of each of the planets by means of amazing feats of human engineering across billions of miles, and into environments of unknown and unimaginable extremes. Getting to the smallest planet in the solar system is anything but easy. Skirting past the Sun at a distance of just 46 million kilometers at the closest point in its orbit, Mercury is a planet that is not only held deep in the gravitational grip of our massive star, but is also moving at an average orbital speed of 48 kilometers per second, by far the fastest orbiting planet in the solar system, and far outpacing the Earth's more leisurely 30 kilometers per second. It needs to whip around this quickly, otherwise it would have fallen into the Sun's embrace long ago. But the combination of its speed and position make it a planet that's immensely difficult to get close to, and even harder to get into orbit around. In order to do so, you have to travel fast enough to catch up with Mercury, but not so fast that you cannot somehow slow down to prevent a headlong descent into the Sun. And that challenge has meant that until relatively recently, it was the least explored of all the terrestrial planets. For many decades, our first and only close-up glimpse of the innermost rock orbiting the Sun came from the Mariner 10 spacecraft, when on 3 separate occasions in 1974 and 1975, it briefly flew past Mercury. This was the first spacecraft to use another planet to slingshot itself into a different flight path, using a flyby of Venus to bend its trajectory, to allow it to enter an orbit that would bring it near enough to Mercury to photograph it close up. Clad in protection to ensure it could survive the intense solar radiation and immense extremes of temperature, Mariner 10 was able to send back the first detailed images of Mercury as it flew past at just over 200 miles above its surface. It passed by the same sunlit side of Mercury each time, so it was only able to map 40 to 45% of Mercury's surface. The spacecraft took over 2,800 photos, which gave us never-before-seen views of the planet's cratered, moon-like surface, a surface that we had never previously been able to fully resolve through Earth-based observation. Despite the beauty of the pictures taken, it wasn't the images from Mariner 10 that really surprised us. It was the data the probe collected relating to Mercury's geology. which pointed to a much more surprising history of the planet than had previously been imagined. Mercury, it seemed, was far from being just a scorched husk. Mariner was able to sense the remains of an atmosphere consisting primarily of helium, as well as a magnetic field and a large iron-rich core, opening a mystery that would remain unexplored for another 30 years. As it flew past Mercury for the last time on the 16th of March 1975, the transmitters were switched off and its contact with Earth silenced. Mission completed, Mariner 10 began a lonely orbit of the Sun that, as far as we know, continues to this day. At first sight, many things about Mercury simply don't make sense. During its 88-day orbit around the Sun, it travels in a lopsided elliptical orbit, which means it can be as far away from the Sun as 70 million kilometers, but occasionally as close as 46 million kilometers. This is by far the most irregular of orbits of all the planets. But it is not the end of Mercury's oddity. Temperatures at midday can rise to 430 degrees Celsius on the surface, but at night, because it's a small planet and it has no atmosphere, temperatures fall to minus 170 degrees, giving it the greatest temperature swing of any known body in the solar system. Its rotation is also unusual, gravitationally locked to the Sun in what is known as a 3-to-2 spin-orbital resonance. This means the planet spins precisely 3 times on its axis for every 2 orbits, which in turn means that its day is twice as long as its year. In effect, you could be travelling over its surface at walking pace and keep the Sun at the same point in the sky as you strolled through eternal twilight. As planetary scientist Nancy Chabot explains, a day on Mercury is not like a day on Earth. It has a very unusual orbit. It has to go around the Sun twice to have one complete solar day on the planet, where the Sun goes from directly overhead to directly overhead. And this actually takes 176 Earth days. Because of the planet's orbit, there are places on the Mercurian surface where a hypothetical observer would be able to see the 2.5 times larger in the sky Sun appear to rise and set twice during one Mercurian day. It rises, then arcs across the sky, stops, moves back towards the rising horizon, stops again, and finally restarts its journey towards the setting horizon. Most of Mercury's anomalies can be explained by the orbital mechanics of its journey around the Sun, except, that is, for the odd elliptical orbit that takes it on such an oval-shaped, elongated course. This irregularity has puzzled astronomers for centuries, and hints at an ancient planet that was very different from the Mercury we see today. To truly begin to understand Mercury's history, we had to wait nearly 40 years before we could return to her. On the 18th of March 2011, NASA's Messenger spacecraft became the first to enter Mercury's orbit. And over the next 4 years, it succeeded in not only photographing 100% of the planet's surface, but also collecting extensive data on its geology. But before any of this could happen, Messenger had to take perhaps the most circuitous route in the history of our exploration of the solar system. Just passing close to Mercury to take a few snaps, as Mariner 10 did, is hard enough. But actually entering into its orbit was thought to be either too difficult to achieve or too costly to execute, as cosmochemist on the Messenger mission Larry Nittler explained. There are 2 major challenges to getting a spacecraft into orbit around Mercury: gravity and money. When you go from Earth to Mercury, you're falling into the gravitational well of the Sun, which makes you accelerate faster and faster as you get closer. And if you were to go straight from Earth to Mercury, this means that you would basically just zip right by the planet, or you would need to bring an incredible amount of fuel to put the brakes on, more than you could actually afford. A number of missions never made it further than pencil and paper, while others floundered and failed at the proposal stage. It was only when Chen Wan-yen, a NASA engineer from the Jet Propulsion Laboratory, JPL, provided a trajectory that could not only get a craft into orbit, but could do it at an estimated bargain bucket cost of $280 million, that the Messenger mission could really begin to take flight. Taking off from Cape Canaveral on the 3rd of August 2004, Messenger began a 6-year, 7-month, 16-day journey to Mercury that would take it on a 7.9 billion kilometer trajectory before it entered into orbit around the smallest of all the planets. To arrive at Mercury with the right speed and on the right course would require a complex route that would entail a number of gravity-assist maneuvers around the Earth, Venus, and Mercury itself to reduce the speed of the craft relative to Mercury. So, combined with the brief firing of its large rocket engine to finally insert it into orbit, this mission profile allowed Messenger to complete its voyage without the need to carry the vast reserves of fuel required to slow its passage through the firing of rockets. This design made the craft lighter and cheaper, but ultimately much slower. Almost 7 years was a long time to wait for the team patiently charting its progress across the stars. Larry Nittler described Messenger's course as sneaking up on Mercury by taking a 7-year journey, flying around the Sun many times, doing multiple flybys around Mercury and Venus, and each time transferring some of the craft's speed and energy to the planet, so it could slow down, so that when we finally got to Mercury after 7 years, we were able to fire our engine just a little bit to slow down even more and get captured by the weak gravitational field of the planet. Appropriately, when Messenger finally entered into Mercury's orbit at 0045 UTC on the 18th of March 2011, the path it settled into was highly elliptical. This orbit took it on a 12-hourly cycle from 200 kilometers above the planet's surface to 10,000 kilometers away from it. It may seem like an odd orbit for a craft with the singular aim of getting as close to Mercury as possible, but this was an essential part of the design of the mission, vital to protect Messenger from the fierce heat radiated by the scorching hot surface of Mercury. The sunlight reflected from the surface is so powerful, it would have literally melted the solder holding the spacecraft together if it wasn't given time to cool down between its closest approaches to the planet. Protected by an enormous ceramic solar shield and its eccentric orbit, Messenger could begin its work. For 2 years, the spacecraft mapped pretty much every bit of the surface of Mercury, and the images beamed back to Earth revealed a planet that's been in the firing line for billions of years. Too small to hold on to an atmosphere that might protect it from meteorites, and lacking any processes to recycle old terrain, Mercury's ancient surface is the most cratered place in the solar system. The Mariner 10 mission had enabled scientists to see about half of the planet, so the first real glimpses into the terrain of Mercury came from the flybys of Messenger. As planetary scientist Nancy Chabot explains, before Messenger, we had only seen 45% of the planet, and we saw some stuff during the flybys before we went into orbit. But after orbiting the planet, we've now mapped 100% of the planet and seen nearly everywhere. There are some permanently shadowed regions which are still mysterious, but after mapping the full planet, we have a good idea of what the surface looks like, and craters are absolutely a dominant landform. This planet has been sitting there for billions of years and been hit over and over, and it hasn't had a lot of processes to destroy those craters. Amongst the thousands upon thousands of craters on Mercury, the largest by far is Caloris Planitia, a lowland basin 1,525 kilometers in diameter that is thought to have formed in the early years of the solar system around 3.9 billion years ago. It was first spotted as Mariner 10 sped past in 1974, but due to the trajectory and timing of the craft, only half of it was lit, so the full character of this crater remained a mystery for another 30 years, until Messenger could photograph it in all of its glory. Taking one of its very first photos, Messenger revealed Caloris to be bigger than had been previously estimated, encircled by a range of mountains rising 2 kilometers from the Mercurian surface, whose peaks create a 1,000-kilometer boundary around the lava plains within. On the other side of the mountains, the vast amount of material that was lifted from the planet's surface at the moment of impact formed a series of concentric rings around the basin, stretching over 1,000 kilometers from its edge. The collision that created Caloris hit Mercury with such force that it also had more global consequences. Messenger photographed in great detail an area named, in the not particularly scientific vernacular, the Weird Terrain, a region at the planet's diametrically opposite point, the antipode to Caloris. This area of strange geological formations, distinct from the rest of the surrounding terrain, was likely created by the seismic shock wave of the Caloris impact, reverberating through the whole of the planet. Right up until the end of its mission in 2015, Messenger continued to uncover many of Mercury's secrets, including a few very particular surprises. Using a combination of photography, spectroscopy, and laser topography, Messenger revealed tantalizing evidence that even this close to the Sun, water ice can exist on the surface of a planet. Even though the Sun blasts much of Mercury's surface, the tilt of its rotational axis is almost zero, so there are craters and features around the planet's poles that never see direct sunlight. Combined with the lack of atmosphere, these regions are forever exposed to the freezing temperatures of space. And it's in this environment that Messenger was able to record the clear signature of water ice. Here, in the eternal night of a polar crater, it's cold enough for ice to survive for millions of years, just meters away from the savage ferocity of the sun's light. However, Messenger's most startling discovery was still to come. The mission objectives had been developed to explore the deep history of Mercury and provide data to test against our theories of the formation and early life of the planet. Messenger was equipped with a collection of spectrometers designed to analyze the composition of Mercury at different depths. The Messenger team had worked on a detailed set of predictions outlining the chemistry of the planet. But as the spacecraft began to sniff at the Mercurian surface, it soon became clear that our assumptions had not been quite right. As the gamma-ray and X-ray spectrometers analyzed the elements on Mercury's surface, they began to measure the unexpected characteristic signature of a number of elements such as phosphorus, potassium, and sulfur at much higher levels than they were expecting. Up to this point, the working hypothesis had been that during the formation of Mercury and all the rocky planets, as the rock condensed and combined to form the planet, the heavier elements like iron would sink towards the center, forming the bulk of the core, while the lighter elements, such as phosphorus and sulfur, would remain near the surface. These more volatile elements would then be expected to be stripped away from the surface, particularly on a planet like Mercury, which is so close to the Sun. And yet the Messenger data confirmed high levels of potassium, and sulfur was detected at 10 times the abundance of the element on Earth or the Moon. Both are volatile elements, easily vaporized, and when this close to the Sun, they simply should not have survived the planet's birth. On top of that, the Messenger data confirmed what we had long suspected about the structure of Mercury, that it is the densest of all the planets, with a massive iron core making up 75% of the planet's radius, compared to just over 50% here on Earth. The core creates a strange lopsided magnetic field, indicating that the internal dynamics of the planet are different to anything we have seen before. All of this adds up to making Mercury something of a mystery, as nothing quite accords. The eccentric orbit, the abundance of volatile elements on the surface, and the oversized iron core all point to the planet having a history far more complex than was first imagined. And the only explanation to make sense of the Messenger data is that Mercury was not born in its current sun-scorched position. It has long been supposedly known that the orbits of the planets are eternal, stable loops that sustain the structure of the solar system in an endless rhythm. But everything we are learning now suggests that this is far from the whole story. Mercury, like all 4 of the rocky siblings, was formed of molten rock. A few million years later, as the young planet began to cool, its crust solidified, and its journey around the Sun transformed from being part of a swirling cloud into a clearly defined passage, an orbit. The path the infant Mercury travelled, however, was most probably far removed from the course it now holds. The young Mercury was born not as the closest planet to the Sun, but at a much greater distance, far beyond the orbit of Venus, beyond Earth, perhaps even beyond Mars. This was a planet that came into being in the mildest region of the solar system. It was far enough away from the Sun to allow volatile elements like sulfur, potassium, and phosphorus to be folded into its first rocks without being vaporized away by the heat of the Sun, but maybe near enough for its surface to be warmed, perhaps even just the right amount for liquid water to settle on its surface. This may well have been a planet big enough to hold an atmosphere, a watery world upon which all the ingredients of life could well have existed. Mercury, it seems, really did have its own moment in the Sun. But these hopeful beginnings were not to last. Today, it's hard to imagine the planets in any orbit other than our night sky. They feel eternal, permanent, and so it's natural to think of the solar system as a piece of celestial clockwork, a mechanism running with perpetual and unchanging precision, marking out the passage of time. In time frames that we can comprehend, days, weeks, months, and years, the motion and trajectory of the planets is just that, clockwork. We use these markers to plot out the 24 hours of a day, 365 days of a year, and the lunar cycle is, of course, intimately linked to our months. Beyond that, Newton's laws of universal gravitation, first described in 1687, allow us to this day to plot out the trajectories of all the heavenly bodies far into the future and back into the distant past. This predictability of motion is what allows us to plot great astronomical events, such as eclipses and transits, far into the future. It's why, for example, we can predict that on the 14th of September 2099, the Sun, Moon, and Earth will be in precise alignment to create the final total solar eclipse of the 21st century across North America. But 100 years ahead or behind us is nothing more than a proverbial blink in terms of the life of the solar system, and over longer durations the clockwork becomes a lot less reliable. If there was only one planet orbiting one star, for example if Mercury was the orphan child of the solar system, we would be able to calculate precisely the gravitational force between Mercury and the Sun, and to plot Mercury's orbit around the Sun with essentially infinite precision. But add one more planet into our rather vacant imaginary solar system, let's say we make it Jupiter, so there is now a gravitational force between all three objects, the Sun, Mercury, and Jupiter, and it's no longer possible to calculate exactly where they're all going to be in the future, or where they were at some point in the past. When there are more than two objects in play at any one time, you have what physicists call a chaotic system. It means the planets can push and pull one another, moving entire orbits in ways we simply cannot predict. So the further we look back in time, the less certain we are of the position of any of the planets. Our mathematics fails, so instead we have to rely on circumstantial evidence to piece together a picture of the past. In the case of Mercury, it's the evidence from MESSENGER detailing the levels of volatile elements like potassium and sulfur that enable us to begin to understand the early life of the planet and infer that Mercury must have begun life further out in the solar system than it finds itself today. So what happened next? How did a planet that began its life in the sweet spot of the solar system end up in the scorched interior? The answer lies in the other clue MESSENGER confirmed for us, Mercury's massive iron core. Relative to its size, Mercury has the most massive core of any of the rocky planets. 75% of its diameter and almost half of its mass is molten iron, compared to around just a fifth of the mass of the Earth. We've suspected the oddity of Mercury's composition for well over 150 years, And that's because of some brilliant deduction by a German astronomer called Johann Franz Encke, who determined the mass of Mercury by measuring the gravitational effect it had on a passing comet, a comet that we now call, unsurprisingly, Comet Encke. With an approximation of the planet's mass, we are able to calculate the density of the planet, and with that calculation, approximate its composition. So we've known for some time that Mercury is odd, but only with the arrival of MESSENGER did we begin to reveal just how odd the smallest planet actually is. By accurately measuring Mercury's magnetic field, we've been able to confirm that far from being a geologically dead planet, Mercury has a dynamic magnetic field driven by an internal force, indicating that the core is at least partially liquid. This goes against the conventional thinking of planetary dynamics, because we would expect a planet as small as Mercury to have lost its internal heat long ago. Just as Mars lost its heat because of its size, we would have expected the core of Mercury to have cooled and solidified. But MESSENGER's data proved otherwise. By combining precise measurements of Mercury's gravity field with the extraordinary mapping of its surface, MESSENGER found that Mercury's structure is unique in the solar system. It appears to have a solid silicate crust and mantle above a solid layer of iron sulfide, which surrounds a deeper liquid core layer, possibly with a solid inner core at the center of the planet. This challenges all the theories about its formation. 4.5 billion years ago, we know that the inner solar system was in turmoil. In the middle of it all, the newly born Mercury found itself orbiting far out from today's intimate proximity with the Sun, surrounded by rocky debris and scores of planetary embryos all jockeying for position. The young solar system was still a place where planets could live or die. But it wasn't just the rocky planets that found themselves disturbed. Jupiter, the largest and oldest of all the planets, was on the move. And when a planet of that size shifts its position, there are almost always casualties. But for now, all we need to know is that the evidence suggests that the juvenile Mercury was kicked by the gravitational force of Jupiter on an inward trajectory, finding itself flung in towards the Sun and into the path of danger. In the crowded orbits of the early solar system, such a change of course was fraught with danger, and all of the evidence indicated that this was the most violent and defining of turns in Mercury's history. As the planet swerved inwards, it collided with another embryonic world and shattered. Today we see the evidence of this ferocious collision in the strange structure of this tiny planet. A giant core has been left behind, the exposed interior of a planet that had much of its outer layer, its crust mantle, stripped away and lost to space in the aftermath of the collision. This collision not only transformed the physical characteristics of the planet, but also knocked Mercury further inwards on a lopsided trajectory that we see reflected in the most elliptical orbit of all the planets. Although we cannot be certain of these events, it's a brilliant piece of scientific deduction to use the evidence we have to create a plausible scenario of events that happened unimaginably long ago. Events that drove the first rock from the Sun from a position full of potential to a place much too close to the Sun to support any form of life. An opportunity lost. After 4 years of observation and its brilliant discovery of Mercury's ancient past, MESSENGER finally ran out of fuel on the 30th of April 2015, and added yet another crater to this tortured world that once held such promise. Shrouded in an unbroken blanket of cloud, the next rock from the Sun tells a very different story. Over 50 million kilometers beyond Mercury lies a world that at first sight has the potential to be far more Earth-like than her scorched inner companion. Venus is perhaps the most mysterious of all the planets. Lying on the inner edge of the so-called habitable zone, this is a planet that holds its secrets close. For centuries, it has teased us with its brightness in the early morning and early evening sky. It's so bright because it's a large planet about the same size as the Earth. It's not too far away from us either, and the clouds that shroud it are highly reflective, reflecting 3/4 of the light that hits them. That's the frustrating but tantalizing thing about Venus, because even when you look at it through a big telescope, it is featureless. You never see the surface, which means that until the 1950s, scientists could only speculate about what lay beneath. In the late 19th and early 20th centuries, many thought that beneath her clouds Venus was hiding a mirror world to Earth. If not home to complex sentient life, then certainly hosting basic life forms. Faced with that impenetrable cloak, our collective imaginations fueled the idea of a living, breathing world beneath the clouds, a shroud that meant for the first half of the 20th century, we lived convinced that we were far from alone in the solar system. Nobel Prize-winning chemist Svante Arrhenius was one of the most renowned scientists to fuel the mythology of what lurked behind Venus's cover. Like many of the scientists of his era, Arrhenius let his curiosity wander into many different realms, including astronomy, and he hypothesized at length about the Venusian environment. Assuming the clouds of Venus were composed of water, he wrote in his book The Destinies of the Stars that a very great part of the surface of Venus is no doubt covered with swamps, creating an environment not unlike the tropical rainforests found here on Earth. Expanding on this picture, he suggested that the complete cloud cover of the planet created a uniformity totally unlike the extremes of weather that define different parts of the Earth. In Arrhenius's imagination, this stable environment, with a consistently uniform climate all over the planet, meant that any life on Venus lived without the evolutionary pressures of changing environments that drive natural selection here on Earth, leaving Venus in an evolutionary limbo akin to the Carboniferous period. Describing a world full of prehistoric swamps and dark forests, Arrhenius created the perfect canvas for science fiction writers of the time to conjure up a menagerie of curious life forms lurking beneath the clouds. Today, Arrhenius is far less known for his fertile imaginings on the wildlife of Venus than he is for his work on the climate of Earth. In 1896, he was the first scientist to use basic principles of chemistry to demonstrate the impact that the atmosphere can have, in particular levels of carbon dioxide, on the surface temperature, a process that was called the Arrhenius effect, but is now known as the greenhouse effect. An effect that would not only have profound consequences for our understanding of our impact on our own planet, but would also be vital in explaining the true nature of Venus beneath the clouds. By the 1920s, as ground-based technology improved, we stopped painting the surface of Venus with our imaginations and started filling in the gaps with facts. The first spectroscopic analysis of the planet's atmosphere suggested that it wasn't water or oxygen that filled the clouds of Venus, so some thought this hinted at an arid desert land beneath. Others speculated that formaldehyde filled the air, leading to the belief that Venus was not only a dead planet but a pickled one too. But come the 1950s, the true nature of Venus began to be revealed, as more accurate Earth-based observations suggested the presence of overwhelming levels of one defining gas in the Venusian atmosphere. This was not a planet shrouded in clouds of water and oxygen, nor pickled in formaldehyde. This was a planet engulfed in a blanket of carbon dioxide, and as Arrhenius had demonstrated on Earth, this almost certainly meant that whatever lay beneath the clouds, the heat would be beyond the limits of even the most resilient life forms on Earth. As the first spacecraft were being built to explore our sister world, it was becoming increasingly clear that visiting Venus would be far from easy, and she would be far from welcoming. In the early 1960s, the Soviet Union began a series of missions under the program name Venera, which attempted to explore the atmosphere and surface of Venus directly for the first time. The initial launches of the Venera program failed before they had even left Earth's orbit, but within a couple of years the program began to slowly see some success. Venera 1 was successfully launched on the 12th of February 1961. Designed as a flyby mission, it is thought to have passed within 100,000 kilometers of Venus, but a total telemetry failure on the craft meant that no data was returned to Earth. As far as we know, Venera 1 is still in orbit around the Sun to this day. Venera 3 attempted to go a step further, and was designed to enter the Venusian atmosphere to take the first direct measurements. However, on crossing the atmospheric boundary, the probe's systems failed, and no data was returned as it plummeted towards the ground. All that was left for Venera 3 was the historic position as the first human-built object to crash into another planet's surface. Despite multiple failures, the Soviets didn't give up, and in October 1967, Venera 4 entered the atmosphere of Venus and sent back data supporting the Earth-based observations, revealing for the first time that the blanket of clouds surrounding Venus was made up of primarily carbon dioxide, 90 to 95%, 3% nitrogen, and just trace amounts of oxygen and water vapor. Venera 4 confirmed beyond all doubt that this was no second Earth. As it descended through the thick clouds, the temperature rose to 262 degrees Celsius. The atmospheric pressure increased to 22 standard atmospheres, 2,200 kPa, and this was still 26 kilometers above the surface. As Venera 4 parachuted its way down to the surface, it provided data to Earth while confirming its own imminent death. This was a spacecraft that was not designed to survive the intense pressures and temperatures it was measuring, let alone the lack of the water landing it was designed for. The craft failed during the descent and was lost long before it reached the surface. Gradually, through the following missions, the Soviet scientists began to overcome each and every challenge Venus put in front of them. Venera 7 was built to survive the most violent of landings, and even though its parachute failed, it made it to the surface intact in 1970 and was able to use its damaged antennae to transmit limited temperature data for 23 minutes before it expired. Venera 9 not only made it to the surface and operated for 53 minutes in October 1975, but was also the first craft to successfully deploy its camera on the ground and transmit an image back to Earth. In the first ever picture taken from the surface of another planet, the black and white fractured image revealed a rocky, desolate landscape, with measurements confirming it to be a blistering 485 degrees Celsius, with an atmospheric pressure of 90 atm crashing down. By the time Venera 13 launched on the 30th of October 1981, the ambition of the missions and the confidence in delivering data from the surface had been radically transformed. Venera 13 functioned for 127 minutes in recorded temperatures of 457 degrees Celsius and a pressure of 89 Earth atmospheres. The probe's cameras deployed, taking the first color image from the surface of Venus. Spring-loaded arms measured the compressibility of the soil, while a mechanical drill arm took a sample of the Venusian surface that was analyzed by an onboard spectrometer. If that wasn't enough, onboard microphones were deployed to record the vicious winds that were assumed to be whipping the surface of Venus, the first ever recording of the sound of another planet. As the Venera missions came to a close in 1983, not even the smallest doubt remained of Venus's hostility. Far from the benign water world we had once imagined, the reality was that this was not a sister we recognized. In our search of the heavens for a place like home, we'd found a toxic, fiery hellscape. Venus is an enigmatic world, almost Earth-like in size, position, and potential, and yet as far from paradise as it's possible to imagine. If Mercury's story is one of catastrophic orbital change, and Earth's of balance and stability, the story of Venus is a tragedy, a tale of subtle yet relentless decline. So why did it all go wrong for Venus? Why did a world born with such similarities to the Earth take such a different path? To answer that, we need to look beyond the tortured planet we see today and go back to a time when Venus was a young, thriving planet. 4 billion years ago, Venus was a familiar world, a world created from the same dust as the Earth, born just about the same size, and settled into an orbit that seemed just far enough away from the glare of the sun to allow a precious process to begin to take hold. In almost every conceivable way, Venus's early life mirrored that of our own world. As its newly formed crust settled and cooled from the violent heat of its birth, an atmosphere began to grow around the young planet, fed by gases bubbling up from the molten rock below its surface, as well as captured from the clouds of gas and dust it swept through on its orbit around the Sun. Clinging to the young Venus, this thin layer of gas would have certainly contained nitrogen, oxygen, and carbon dioxide. But most intriguing of all, we are certain it would have also contained large amounts of water vapor. High in the Venusian atmosphere, this water vapor eventually cooled enough to change state from vapor to liquid. And with that transformation, a process began that perhaps for the first time on any of the planets would have seen the conditions become just right for droplets of liquid water to take shape and begin falling from the Venusian sky. These were the first rains of the solar system, showering down onto the dry plains of Venus. Gradually these rains would have not just fallen but flooded the surface. Rivers would have flowed, and shallow oceans taken hold of large swathes of the planet's surface. Venus, perhaps before even the Earth, became a water world, a planet with skies full of clouds and a surface full of oceans, feeding the cycle of water around this young planet. How can we be certain this blue version of Venus existed? Unlike Mars, where we can see the evidence of its watery past etched onto its surface, we have no such direct evidence of the presence of liquid water on the surface of Venus. The only physical evidence we have that suggests the planet's watery past comes from measurements taken by NASA's Pioneer Venus spacecraft back in 1978. One of its most surprising discoveries revealed an unexpected amount of deuterium, heavy water, in the atmosphere compared with hydrogen. This DH ratio is far smaller on Venus than it is on Earth, and that's interesting because when the two planets formed, the ratio would have almost certainly been the same. Because hydrogen is far more easily lost from an atmosphere than deuterium, this smaller ratio suggests that Venus has lost a lot more water than the Earth over its lifetime, the signature of a long-lost primordial ocean, as cosmochemist Larry Nittler explains. Scientists believe that Venus once had a lot of water in its oceans, but lost it over time, and perhaps in oceans as recently as 1 billion years ago. The reason we can tell this is from the isotopic composition of hydrogen measured in its atmosphere by spacecraft. Now, hydrogen has 2 flavors of isotopes. Whereas most hydrogen atoms are just a single proton in the nucleus, some, a small fraction, are what we call deuterium, that have a proton and a neutron, so they weigh twice as much as the regular hydrogen. What happens when you have evaporation of water from a planet, or the atmosphere, is that the water molecules that contain hydrogen are much lighter than the water molecules that contain deuterium, so they evaporate more easily and can be lost more easily. So over time, as you evaporate water, deuterium-bearing molecules stay behind relatively to the regular ones, and you build up a deuterium to hydrogen ratio. And by back-calculating from the measured ratio today, we can figure out how much water has been lost over the billions of years of evolution, and on Venus, it's quite a lot. None of this is solid proof, but it does begin to point us in one direction, and with no further exploration of the surface, we've had to rely on an accumulation of indirect evidence to begin to paint a more detailed picture of Venus's watery past. As with almost all of our understanding of the planets, the evidence that built this picture has been accumulated through decades of exploration. Starting with the Venera mission's first touchdown on the planet, to the Pioneer Venus orbiter, and to the more recent Magellan mission, which not only relayed extraordinary radar soundings of the surface of Venus, but provided the first full topographical map of the planet collated over a period of 4 years in orbit. Combining all of the data that has been accumulated over decades of exploration has allowed us to peer deep into the planet's past, using the same tools that enable us to model the future of climate change here on Earth. to create climate models of Venus in the past, present, and future.